We start chapter 3, section 3.1, Extrema on an interval. So now that we've learned how to find derivatives of functions, what we're going to do next is find applications of finding derivatives of functions. Now, extrema comes from the Latin. When you have extreme values, in Latin we have the noun extremum, which is singular. Extrema is plural. So you'll see the same thing with maximum. A maximum is a noun, but it comes from the Latin. But more than one maximum in Latin is maxima. More than one minimum, minima. So they drop the um and they add the a. So don't get weirded out by the vocabulary there. Extrema on an interval means to find the extreme values on an interval, whether it's an open interval or whether it's a closed interval for a function. All right, one of the most useful things we can learn from our function's derivative is whether the function assumes any maximum or minimum values on a given interval, and where these values are located if, I went from plural to singular here, so I kind of crossed it out to go back to plural, if they do. Now let's think of some possibilities. What's the most effective dose of medicine? What's the least expensive way to operate a piece of machinery? So in this world, probably more than at any other time, we want to maximize or minimize whenever we can. We want to maximize profit. We want to minimize cost. We're always looking for the best. When you are listening to the TV, another good excuse for drinking coffee. When we were looking for listening to the television, they talk about the best basketball player. They talk about the worst of the presidential candidates and so on. So we're always looking for the extreme values. All right, so we're going to look at two different kind of extrema. The first type is called absolute extrema, or sometimes kind of more old school, global extrema. All right, and absolute extrema, as you might imagine, means it is the largest, it is the smallest on the interval. Let f be defined on an interval I containing c. F of c is a minimum of f on I. That means the function f on the interval I, if f of c is less than or equal to f of x for all x in I. F of c is the maximum of f on I if f of c is greater than or equal to f of x for all x on I, or in I, as an element of I. So when we are, excuse me again, when we are looking for these values, what we're going to do is we're going to look for values that are always smallest, always largest. The maximum and minimum of a function on an interval are called the extreme values, or the extrema. There's that word again, of the function on the interval. The maximum and minimum, by the way, when they just use the words maximum and minimum, they're talking about the absolute or the global extrema. The absolute maximum, the absolute minimum. So the minimum and maximum of a function on an interval are also called the absolute or global maximum minimum on the interval. So if they don't put the adjective in front of it, it's assumed that it's there. Okay? So it's always the smallest, always the largest. And these are the values. These are the y's. These are not the x's. These are the x's that, this is the x that finds the smallest y, or the largest y value. So let's look at an example, kind of a simple one. It says, consider y equals x squared on the interval from negative infinity to infinity, then on the interval from 0 to 2, then on the interval from 0 to 2 included, then on the interval from 0 to 2 including the 2 but not the 0, and then on the interval from 0 to 2 not including either endpoint. Find the absolute extrema if they exist. Now, from negative infinity to infinity, as you can see by these arrows here, this is going to go up and up forever and ever and ever. There is no maximum y value. It's unbounded. However, there is a minimum value down here at the origin, because that's the smallest y value of any point on this curve, is this vertex. So we have an absolute minimum of 0 at x equals 0. Now, sometimes in the textbook, when they ask for the absolute maximum or absolute minimum, they'll say specifically and use the word value. Okay? And in this case, it says find the absolute extrema, which is finding the absolute maximum, absolute minimum. So they actually want just this part right here. But it's okay to state where it exists, and sometimes you'll even see it written as the ordered pair. I like this a little bit better. Kind of depends on the way, if they ask for a minimum point, sometimes they'll say it in that terms, and then you would write the ordered pair. All right, now, I'm going to change this. I'm going to change this by only looking at a certain point, or a certain part of this curve here that I have here, this parabola, from 0 to 2. Now, here's 2. And here's, of course, 0. So from 0 to 2, inclusive, would be that part that I have outlined in red there. Hopefully you can see that all right. Well, in this case, I'm going to have both an absolute maximum and an absolute minimum. The absolute minimum is still 0, 0. So it's an absolute minimum of 0 at x equals 0. But I'm also going to have an absolute maximum this time, because on this part here that's outlined in red, you can see that the largest y value of any point on this curve in red here is at 4, and that happens when x is 2. So I have an absolute maximum of 4 at x equal 2. Now I'm going to change the problem again. This time I'm only going to include the endpoint 2, not the endpoint 0. So it's going to look more like this. I'm going to try to do this in green. Hopefully you'll be able to follow it okay. I filled in the dot here. It's an open dot here. Well, this does not have a minimum value because there is no, how do I want to say it? There is no smallest number that's greater than 0 because the set of real numbers is dense. So what we're going to do here is we're going to say, no, I'm just going to go ahead and write it out this way. No absolute minimum, but we still have up here, we have an absolute maximum of 4 at x equal 2. Oh, back here. No absolute maximum. Okay? So now, what's left from 0 to 2? Now, let's see. Here I got a blue pen. Let's see if this blue pen will work. That would look more like this. Hopefully you can see that okay. In this case, from 0 to 2, non-inclusive, there is no smallest, there is no largest, so there are no absolute extrema. So it's kind of based on not just the function, but the replacement set of the function, or the domain of the function, or what interval you're looking at of the function. All right, now let me move this out of the way. And the next one up is a very important theorem called the extreme value theorem. This has got another name, but off the top of my head, I can't remember what it's called. It's named after a mathematician. I'll have to double check that for you guys. All right, the extreme value theorem says if f is continuous, notice it has to be a continuous function, on a closed interval from a to b, then f has both a maximum value and a minimum value on the interval. Now, it doesn't tell us what the maximum and the minimum values are, but it says that they do exist. So here's another example of an existence theorem. It says that these values exist, but it doesn't tell us exactly how to find it. We're going to have to use some algebra to do that. So I have an example, and I went ahead and I graphed this. It says find the absolute extreme values of f of x equals x squared minus 4x plus 5, parabola, on the closed interval from -1 to 3. Now, because it's a polynomial function, I know it's continuous. All polynomial functions are continuous. So that part is met. And I have a closed interval. I have a closed interval from -1 to 3. So what I did here, and I tried to anyway, here's -1. -1, you're way up here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is -1, 10. And then over here at 3, this is 3, 2. And of course the vertex is down here. This is 2, 1. So if I want to find the absolute extreme values, I have a closed interval, I have a continuous function, they exist. Now, at this point, we're going to use the graph to help us. But very soon, I'm going to show you how you can use the derivative of the function to find these values. We won't even need a graph, but we'll need one for right now. So I have a continuous on a closed interval. Therefore, extreme value theorem guarantees extrema, absolute extreme. Okay. Now I went ahead and wrote that out because I want to emphasize the fact that this criteria has to be met before we can actually apply it. Now I have the graph, so that's kind of a giveaway, and you can see that the largest y value is going to be 10 and the smallest y value is going to be 1. But I go ahead and I set up the preliminaries. So I have an absolute maximum of 10 at x equal -1, and I have an absolute minimum of 1 at x equal 2. Okay, now you kind of look at this guy sitting over here. Even though he's not a maximum, I mean, to the right of 2, he's kind of top dog. So we're going to have to give this guy a name as well. And that's what I want to consider here in this next diagram. We have a graph, y equals f of x, and it's on a closed interval from a to b. And as you can see, I've got this set up so that it has it's continuous, and I've marked 5 points. Now notice here, at A at this endpoint I've marked, at B at this endpoint I've marked, but I've marked 3 others. And in all 3 cases, I hope that you can see this here, at all 3 cases I've marked points that are kind of like at the top of the hill or the bottom of the valley. If you were to draw a tangent line to these 3 points, they'd all be horizontal. I hope you agree with that. Okay, now we do have an absolute maximum. The absolute maximum, I don't know what it is because I didn't mark values over here, but it occurs when x is a. It would be f of a. And I do have, based on this diagram, an absolute maximum. I think I said, hopefully I said minimum here. Absolute minimum at x equal a of f of a. I have an absolute maximum at x equal e of f of e. But what about these 2 guys here? Okay, they're kind of like I was showing you over here on this guy. They're kind of like a maximum in this region, or a minimum in this region, just not for the entire domain. Well, that gives us the second type of extrema that we're going to talk about, and they're called relative or local extrema. Okay, local is again more of the old-fashioned way of saying it. We usually use the term relative extrema. Let C be an interior point of the domain of the function of f. Then f of c of a is then f of c is a first local maximum value of c if and only if f of x is less than or equal to f of c for all x in some open interval. Notice it doesn't say for the entire domain, in just some open interval. So if you go back here and look at where c is at, in this open interval here, do you see, no pun intended, do you see, that at x equals c, right in for these x values, this guy's top dog. That's maximum. So we call him a relative maximum, or a local maximum. Then f of c is a local or relative minimum value at c if and only if f of x is greater than or equal to f of c for all x in some open interval around c, containing c. Well, and again, in this case, let's look at here when x is d. If I look at the open interval here, and I'm going to try to make them a little darker so you can see what I'm emphasizing. At x equals d, this guy here is bottom of the graph. It's as low as it goes. Okay? So these guys have special names as well. Now, here's the cool thing. All relative extrema, this definition covers the same definition in some ways for absolute extrema. An absolute extrema is a relative extrema, but not necessarily the other way around. All absolute extrema are relative extrema, but not all relative extrema are absolute extrema. It's like back in geometry when they first talked about all squares are rectangles, but not all rectangles are squares. It's just a subset of the relative extrema in this case. So let's move this over to the side. Okay. we can extend the definition of local extreme values or relative. I use local a lot because it's kind of what I was taught, a million years ago. We extend the definition of relative extreme values at an endpoint. At an endpoint, C, let's go way back here. Even though I don't have an open interval on this side, I have it over here. We can extend this here and call this guy a relative, in this case, a relative maximum. At a relative maximum of 2 when x is 3. So we can include the endpoints at C. If the appropriate inequality holds for all x in some half-open domain interval containing C. Also, this is, as I mentioned before, absolute extremum is also a relative extremum. Okay, now here's the definition here of local extreme values. A function f has a local maximum value on its or a local minimum value, and again relative, it can be used at an interior point C of all of its domain, and if f prime of C exists at C, then f prime of C is equal to 0. Now let's think about what this is saying. F prime of C. F is a function. It has a local maximum or a local minimum at some interior point in the domain, call it C. If f prime exists, because it's possible that f prime might not exist at that value, if f prime exists at C, then f prime of C is equal to 0. Let's go back. Remember I was talking about horizontal tangent lines occurring here? F prime, that's the derivative, that's the slope of the tangent line. The slope of the tangent line is 0, horizontal, a horizontal tangent line. All right, so this is how we're going to find relative extreme values and absolute extreme values by using this key definition here, where the derivative of the value is equal to 0. So now, this value C has got a special name if the derivative is equal to 0. It's called a critical number. There are two types of critical numbers. They're going to be defined in this. So we are going to find critical numbers using derivatives. I'm going to give you the definition here in just a second. We're going to find critical numbers by using the derivative, and then we'll be able to determine relative extreme values, relative maximums, relative minimums, absolute maximums, absolute minimums. But again, the graph is a good way to check here. Let f be defined at C. If f prime of C is equal to 0, or if f is not differentiable at C. Now the function is defined at C, but the derivative, you can't take the derivative at x equals C. So the derivative is undefined, for example. Then C is a critical number. All right, really important idea. I don't want to use the term critical and sound trite, but this is a really important idea. We find critical numbers by taking the derivative and setting it equal to 0 and solving, or we look to see what values make the derivative does not exist at, but that the function exists at. These are two types of critical numbers. I'm going to go to this in some detail. When the derivative is equal to 0, okay, these are called stationary critical points, where the derivative is not defined, but the function is. These are called singular critical numbers. All right, now, let me move this up just a little bit. Very important theorem. Fermat's theorem says, or sometimes I think the textbook says that this name of this theorem is the relative extrema occur only at critical numbers. Well, the name kind of tells you what the theorem is all about here, but it's probably better known as Fermat's theorem. It says if f has a relative minimum or a relative maximum value at x equals c, then c is a critical number of f. Now, it doesn't say it the other way around. It doesn't say every critical number gives you a relative max or min, but it says if there is a relative max or a relative min value and it occurs at x equals c, then c has to be a critical number. So we're going to find critical numbers and get a list of them, however many there may be. There might only be 1, there might be 10. Those are our candidates. And then we're going to check to see which ones give us minimums and which ones give us maximums here. All right, so first things up. Find the absolute maximum and minimum values of f of x equals x to the 2/3 on the interval from -2 to 3. All right, so again, right now, we're going to have to probably use some type of a sketch here But I'm going to try to sidestep that for this first example, but I'm going to show you the sketch to back up my work. First thing I'm going to do, notice f of x equals x to the 2/3. This is a continuous function. Okay, and it's a closed interval, so I'm guaranteed an absolute max or an absolute min, and an absolute min, excuse me, the extreme value theorem. So I am going to take the derivative, which would be 2/3 x to the -1/3, which is 2 all over 3 the cube root of x. Now, my derivative can never equal 0 because the numerator is a constant. But my derivative could be undefined, and it's undefined when x is 0. But you'll notice here that 0, which is in the interval, is defined for the original function. So I only have one critical number. I like to abbreviate critical number Cn, and my critical number is x equals 0. Now, some textbooks and some videos will say critical points. So they'll actually write the ordered pair. So if I was to plug 0 in, I would get 0 here as well. So my critical point is 0, 0. But there's no definition in this textbook for a critical point. It's just kind of an easy way to kind of keep track of the critical numbers, but writing them out as ordered pairs, because normally we would be interested in the y value as well. So now I have one critical number, but I also have these endpoints. Remember, when we did another example earlier on, the extreme values occurred at the endpoints, and we're looking for the absolute extreme values. So I'm going to take f of -2, I'm going to take f of 0, and I'm going to take f of 3. These are my endpoints. This is my critical number. I'm going to substitute back into here. Because I have a continuous function and because I have a closed interval, I know that I'm going to have extrema, absolute extrema, occur on this for this problem. So f of -2, I plug -2 in, and I get -2 to the 2/3, which is the cube root of 4. Then I'm going to plug 0 in, and I get 0. Then I'm going to plug 3 in. So I have 3 to the 2/3, which is the cube root of 3 squared, which is 9. Well, that's my smallest y value out of the 3. That's my largest y value out of the 3. All right, so I have an absolute max of the cube root of 9 at x equal 3, and I have an absolute min of 0 at x equals 0. Now, if you graph this, let me go ahead and write the critical number up here as x equals 0. If you graph this, let's see if I have enough space to do it justice here. Actually, I probably should just put it down here. Sorry about this being so sloppy. Should be using a straight edge for a graph anyway. My graph looks something like this. Okay, really rough there. And you can see that this is the largest value, the cube root of 9, which is a little bit more than 2. So I'll put 2 right here. All right, it's a little bit more than 2. And then I have the cube root of 4, which is a little bit less than 2. So this is the largest y value. And of course here at 0, 0, this is where my absolute minimum exists, of 0 at x equals 0. Okay? So the graph is a nice way to check your work. Find the values of the relative extrema for f of x equals 3x to the 3rd plus 6x to the 2nd plus 3x minus 9. I'm going to get Mr. Calculator out to help me with this one, but notice there's no closed interval. This is over all real numbers, so I've got to find my critical numbers here. All right, and since this is a polynomial, I'm going to hope that you will agree that my derivative is going to be a polynomial. This is a continuous function here. So I get 9x to the 2nd plus 12x. Notice how important it is to be able to take a derivative and not just sit there and look at it for a while. Plus 3. And of course the derivative of minus 9 is 0. So my critical numbers, I'm not going to have any critical numbers from, like I did in the last example, which when I had back here at x equals 0, that was defined for the original but not for the derivative. I am going to have only those kinds of critical numbers where my derivative is equal to 0. So I set my derivative equal to 0. I can divide through by 3. And this factors, which is really nice. Looks like a 1 and a 1 and a plus and a plus. So I get x equals negative 1/3 and negative 1. Kind of running out of space here. Now, those are critical numbers. Those are not the values, those are the critical numbers. Here, critical numbers. Let me abbreviate that. I get Mr. Calculator busy here to kind of see what's going on with my graph here. So I'm going to have 3x raised to the third plus 6x squared plus 3x and a minus 9. Okay, so let's see here. All right. Let's see. Maybe we could make this look a little bit easier here. This is kind of tough to tell. Well, we'll do our best. Okay. What happens here is, as you can see, at x equal 1, there's going to be negative 1. Do you see how it kind of peaks up right there at the top? This is really hard for you to see, so let me change the window just a little bit. Let's go from negative 3 to positive 3, and we'll go from negative 10 to 1. Okay, let's see if this makes it a little bit easier here. Do you see how on my graph, this is an S, kind of a shape, a sideways S. This is going to drop down forever and ever. This is going to go up forever and ever. But do you see I've got a little top of the hill here and a little bottom of the hill here, bottom of the valley I should say. So that's where I'm going to have a maximum occur, a relative maximum, and that's where I'm going to have a relative minimum occur. Now what are those values? Well, look right back here. They're at negative 1/3 and negative 1. Negative 1 would be over here. That's where my relative max occurs. Negative 1/3 would be over here. That's where my relative minimum occurs. Now, I'm going to have a relative maximum of, I got to figure it out, at x equal negative 1, I'm going to have a relative minimum of some value at x equal negative 1/3. So now, I've got to take these and I got to plug them back into my function to find the y value. Don't plug them into the derivative, you're just going to get 0. Plug them back, that won't help you anyway. Plug them into the original function because you want the y values of the original function. Now negative 1 doesn't look that bad. That would be negative 3 plus 6, which is 3, minus 3, which is 0, minus 9 is negative 9. On the other hand, negative 1/3 is going to be a little bit more of a pain. 3 times negative 1/3 to the third power plus 6 times negative 1/3 to the second power plus 3 times negative 1/3 minus 9. See, that's 127. Negative 127 times 3 is negative 1/9. And this is going to be 1/9, so this would be plus 2/3. And this is going to be minus 1 minus 9. So it's the common denominator would be 9. That would be 6. That would be 5/9 and a minus 10. So that would be negative 9 and 4/9 if I didn't mess up too bad here. Negative 9 and 4/9. You can check my work and tell me later on if I made a mistake. But that would be my relative minimum value. So it says find the values of the relative extrema. Now if you go decimal on me here, and I don't think there's really any need to because the fractions didn't get that bad. Remember, give me 3 decimal places. Okay. All right, so we're going to scoot on from here. Now we know all about the sine function. It says find the relative extrema. G of x equals the sine of x on the closed interval from 0 to 2 pi. Well, we know we're going to have a maximum and a minimum. In fact, we know so much about sine, we already know what the maximum and minimum values are going to be on the interval from 0 to 2 pi, because that's a full period of the periodic function. I'm going to have a maximum value of 1. I'm going to have a minimum value of -1. But let's go ahead and set this up. I'm going to take the derivative, g prime of x, which is, can you see that okay? I hope so. You get the cosine of x. I'm going to set the cosine of x equal to 0, and that's going to occur. Now remember, we're only interested in between 0 and 2 pi. That's going to occur at pi over 2 and at 3 pi over 2. These are my critical numbers. I also have endpoints to check. Graphically, and I'm hoping that you guys remember a little bit about the graph here of sine, even with the review that we had back in the prerequisite chapter. If this is pi, and we'll say this is 1 here, and this is 2 pi, our graph looks something like this. Okay. I have endpoints that I'm going to have to deal with, but you can see where my max is, you can see where my min is, and they're occurring at those endpoints. Excuse me, at those endpoints, at those critical numbers. It'd be okay if I knew what I was talking about. There we go. So I have an absolute max of 1 at x equal pi over 2. I have an absolute min of -1 at x equal 3 pi over 2. All right, and you say, well, they're asking for relative extrema. Remember, absolute extrema or relative extrema. I just went ahead and got a little bit more in line here because that's the largest value, that's the smallest value. But I also have to consider the endpoints here because we can consider a half open. Let's see, how do I want to say it? An interval that's half open then, at the endpoint there. Something like this. At the endpoint. Nothing over to this side like that. Something like this. Right over here. So that's going to be the largest, that's going to be the smallest. So I did not give myself enough space. I'm also going to have a relative maximum of 0 at x equal 2 pi, and I'm going to have a relative down here, see how it slopes, comes down, a relative minimum of 0 at x equals 0. So I have all of this for this problem because it's asking for relative extrema. Now, when we're looking for extrema, find the critical numbers, and as I mentioned before, they're called stationary if the derivative is equal to 0. They're called singular with an S if the derivative at that value does not exist, but f of c does exist. And even though it's not necessarily a critical number, we need to check the endpoints if the endpoints exist like they did in the last example. All right, so now I have a few more examples to finish, and then hopefully we'll have everybody's questions answered. Now, I want to make sure that I emphasize that at first when you're doing these, don't shy away from using some type of a graph or a sketch to kind of back up your work here. All right, so let's go to this first example, find extreme values. All right, now notice here it says extreme values. Doesn't say relative extreme values, it says extreme values. So these are absolute extreme values here. So what happens? Well, we've got continuous function, closed interval, they're going to exist. Take the derivative. That would be 12x to the second plus 12. I said 12x to the second plus 12 equal to 0. I can factor out a 12. I get x squared plus 1 is equal to 0. Well, wait a minute. That can't be 0. That can't be 0. So there are no critical numbers, so my extreme values are going to occur at the endpoint. So I find g of 0. G of 0 is 0. Oops, cubed. I find g of 2. That would be 4 times 2 to the third plus 12 times 2. So that would be 8, 32, 24, 56, I hope. And so I have a relative, I have an absolute maximum value of 56 at x equal 2, and I have an absolute minimum value of 0 at x equals 0. So everything occurs at the endpoints here. Take the next guy up. This is also a continuous function on a closed interval. H prime of x would be 2 minus, now you do the power rule here, 2/3 times 3 is 2, x to the subtract 1, negative 1/3. So I can already see that this derivative is going to be undefined at 0, but it's defined, the original function is defined at 0. So I know I have a critical number at x equals 0 before I hardly get any work done. This is 2 all over the cube root of x. Hopefully you can see that all right. That's a cube root here of x. So I am going to set this equal to 0 to find if there are any stationary critical numbers. I have a singular one. So let's see, 2 minus 2 over the cube root of x equal to 0 means I have 2 over the cube root of x is equal to 2. And if I multiply both sides by the cube root of x, I get 2 is equal to 2, the cube root of x. If I divide by 2, I get the cube root of x is equal to 1. If I cube both sides, I get x equals 1. So I have 2 critical numbers here. And I have endpoints. So I've got some work to do here. I've got to find h of negative 1. I have to find h of 0. I have to find h of 1. And I have to find h of 3. Now, in all cases here, I have the 2, the 0 and the 2. I have the endpoints, negative 1 and 3. I like to just list them in order from smallest x value to largest x value. That's just the way I do it. So this is going to be 2 times negative 1 minus 3 times negative 1 to the 2/3. Negative 1 to the 2/3 is going to be 1. So this is negative 2 minus 3 is negative 5. Now I'll substitute 0 in. 2 times 0 minus 3 times 0 to the 2/3. This is 0, this is 0, this is 0. Then I plug 1 in. I get 2 times 1 minus 3 times 1 to the 2/3. So this is 2 minus, of course this is just 1, minus 3 is negative 1. Well, right now that's my smallest value. Right now that's my largest value. Let's see what happens at 3. I get 2 times 3 minus 3 times 3 to the 2/3. Oh, this one might take a calculator. So this is 6 minus, now 3 to the 2/3 is the cube root of 9. So this is 3 times the cube root of 9. Now we had the cube root of 9 on a different example. This is a little bit more than 2. 6 minus 3 times a little bit more than 2. This is going to be, this part right here is going to be a little bit more than 6. A little bit. You know, like 0.2. So 6 minus a little bit more than 6 is going to be negative, and it's going to be approximately negative 0.2. I'll get Mr. Calculator out and check it for sure. I probably have this wrong. So let me just make sure of it. 6 minus 3 times, what is that, 9 raised to the 1/3 power. No, I wasn't too far off. About negative 0.240 there at the 3 decimal places. So here's my largest, here's my smallest. So again, no space. I always seem to do that. I have an absolute max of 0 at x equals 0. I have an absolute min of negative 5 at x equal negative 1. Right here. Okay. Try to be neat. Hopefully you're going to be neater with your work than I'm showing you here. Next guy up. Uh-oh. Definitely want to think about doing this one using a sketch to help me here. This part is a multi-ruled function from 1 to 3. I have what looks like a parabola that opens downward, and then from 3 to 5 it looks like I have a line. So let's see if I can come up with a reasonable sketch here. Let's see, 5. Not going to probably get a reasonable one here. Let's see what happens. 1, 2, 3, 4, 5. And let's see, at 1, I'm using this, so at 1, I'm at 1. At 2, I'm at -2. And at 3, although I don't include the endpoint, I would be at -7. Uh-oh, did not make my sketch big enough. So we're going to have to change the scale here a little bit. So let's see, down here -7 at 3. And that's an open circle. Oop, that's an open circle. Okay, now here, if I plug 3 in, I'm going to get -7. That fills in the circle. And then if I plug 5 in, I'm going to be way down here at I'm going to be at 5, -13. All right, well, I've already figured out my absolute extrema here. They're going to occur at the endpoints. If you take the derivative here, you're going to get -2x. And if you set it equal to 0, you're going to get 0. That's not in there. If you take the derivative here of the second rule, you're going to get -3. That's never going to be 0 or undefined. So this is all based on the sketch here. I have to find just the endpoint, so at f of 1 and at f of 5. At f of 1, we figured it out to be 1, and at f of 5, we figured it out to be -13. So absolute max of 1 at x equal 1, and an absolute min of -13 at x equal 5. Sorry this one's taken so long. I just wanted to try to show you enough examples to help you out here. All right, I'm going to scoot this over, and we are practically done. 2 more examples. Now, this is a continuous function. I know it's a continuous function because it's a sum and scalar multiples of continuous function, or difference I should say, and it's a closed interval. So I am going to have to find my critical numbers. This is going to be 2 cosine x minus, now I have to use the chain rule here. The derivative of the cosine of 2x would be opposite sine of 2x times the derivative of 2x, which is 2. This is going to be messy. I have 2 cosine x plus 2 sine of 2x. I'm going to have to set it equal to 0. It's never undefined. So that's going to give me, I can divide through by 2, I suppose, if I want to. That's going to give me the cosine of x plus, now if I divide through by 2, I get the sine of 2x, which is 2 sine x cosine x. Solving trig equations. You've got x, you've got 2x, you've got to get it all in terms of x or all in terms of 2x. I can factor out a cosine of x. That would leave 1 plus 2 sine of x equal to 0. I'm going to set the cosine of x equal to 0. I'm going to set 1 plus 2 sine x equal to 0. All right, the cosine of x is equal to 0 at pi over 2 and at 3 pi over 2. The 1 plus 2 sine of x is equal to 0 when the sine of x is equal to -1/2. And that occurs at, let's see, 7 pi over 6 and 11 pi over 6. So I've got quite a mess here that I have to keep track of. I have 4 critical numbers and I have endpoints. So I am going to have to find f of 0, f of pi over 2, f of 7 pi over 6, f of 3 pi over 2, and k of 2 pi. Nope, no, 11 pi over 6, almost forgot one, and then k of 2 pi. One of these is going to give the largest, one of these is going to give the smallest. Now, if I plug in 0, I get 0 here. Cosine of 0 is 1, so I get -1. If I plug pi over 2 in, the sine of pi over 2 is 1, so that's going to be 2 minus That'd be the cosine of pi, which would be a -1. So I'd have minus a -1. 2 minus -1 is 3. If I plug 7 pi over 6 in, the sine of 7 pi over 6 is -1/2 times 2 is -1. If I plug 7 pi over 6 in there, it's 2 times that. That'd be 7 pi over 3, which is coterminal with pi over 3. Oh, hang on a second. I got to make sure I'm plugging it into the right spot here. Let's see. I may have plugged this into the wrong one. Let's see. That's 2. No, that was right. All right, so that would be -1 minus, let's see, cosine of pi over 3 would be 1/2. So -1 minus 1/2 is -3/2. We have a new smallest value. 3 pi over 2. This is taking forever. The sine of 3 pi over 2 is -1. So that's going to be -2 minus 2 times 3 pi over 2 is 3 pi, which is coterminal with pi. That's 0. So I have -3. Oh, no, not 11 pi over 6. So that'd be -1/2 times 2 is -1. I'm going to write it down so I don't lose track. This would be 11 pi over 3, which is the same as 5 pi over 3. The cosine of 5 pi over 3 is 1/2. So -1/2. So I get -3/2. And then a 2 pi, well, it should get the same thing as I got here. It's 0, but let's make sure. The sine of 2 pi is 0, so that's all 0, minus the cosine of 4 pi, which is the same as the cosine of 0, which is -1. I think I got some symmetry working here. Whew. So I'm going to have to put it up here because I didn't leave myself enough space. I'm going to have an absolute max of 3. Is that 3 or is that -3? Pi over 2. So that's 2 minus pi minus a negative. No, that's it. So and I have an absolute max of 3 when, or at x equal pi over 2. And I have an absolute minimum of -3 at x equal 3 pi over 2, occurring at the critical numbers. All right, there's my answer. What a mess that one is. Just not only just the handwriting, but all those critical numbers to plug in. All right, now we have another function here with a radical in the denominator, and this is an open interval, so it doesn't guarantee us the existence of extrema, an absolute max and absolute min. But let's see what occurs here. I'm definitely going to check this one with a sketch here. First things first, f of x. I'm going to write this as 4 minus x squared to the -1/2 and use my generalized power rule to take the derivative. So my derivative is going to occur at here. Let's see, it's going to be -1/2 of 4 minus x squared to the -3/2 times the derivative of the inside function, which is -2x. So -1/2 times the -2x is x. So I have x all over. I'm going to write this as 4 minus x squared to the 3/2 power. Now, if I set this equal to 0, the derivative is equal to 0 when the numerator equals to 0, so I do have one critical number. That's why I have to kind of check to see if this critical number is going to give me an absolute maximum or an absolute minimum, and I think it's going to probably give me an absolute maximum or an absolute minimum, but we'll see what happens here with the sketch. I need something more than this, and that's what the next section, or excuse me, section 3 is going to help us with in this chapter. Without having to have the graph in front of me, I can determine if I get what type of an extreme value this is going to be. So now let me grab my graphing calculator here, and let me clear out what I had before. So this is 1 divided by 4 minus x squared raised to the 0.5 power. And let's see, let's just do standard here for now. Yeah, that's not very helpful. Let's see if we can do better than that. Let's zoom this in just a little bit here. Let's go from -3 to 3. And let's go from -1 to 4. That should be plenty here. Hang on 1 second there. -1 to 4. Okay, let's see if this graph looks any better. Yeah, it looks like at x equals 0, I am going to get a minimum value here. Now that does almost look horizontal, and that's probably because of the number of pixels on my screen. But because I know I'm getting an extreme value, I have to just plug 0 in here. I'm going to get an absolute minimum of 0 here. If I plug 0 in, I get a half of a half. At x equals 0, I have no absolute maximums. All right. Well, hopefully those extra examples that I did here are going to make it a little bit easier to work the different kinds of problems that you guys have in your assignment and your practice problems. So definitely practice, practice, practice.